Hi everyone, I'm Teddy. I hope you're having a good morning. I'm going to be talking about the embedded side for STT-MRAM. So let's just start off the presentation to explain to everyone what the real difference is between embedded versus standalone memory. So I would say standalone is probably what you have in your mind when you think about memory. This is your hard disk or your SSDs that you interact with often within your computer, because these are the off-chip and sometimes called primary memories that are relatively cheap and big, but they have a problem of being slow. And that's not necessarily due to their own device characteristics, but also they have to interact with your processor units, and that interconnect protocol takes time as well. So you have to go to embedded memory, which is more on chip. What you do here is you integrate your memory directly into your logic processors to get something that's expensive, small, but fast. And the picture here, if you're not familiar with it, is an example of cache, which is one of the more extreme examples of small, expensive, but fast. And what really drove this development through in the past is the processor memory gap. You see, starting in the 80s, CPUs from Moore's law has been scaling in a miraculous speed that the memory industry, while they've also been scaling well, just couldn't quite keep up. And so you need to trade off between elite embedded cores and more usable everyday functions, such as your hard disk. Now, I want to talk in particular embedded non-volatile memory, or ENVM, and their applications. And as you can see here, I've kind of listed it all out for you, but they're generally really exciting for low standby power working memory. What that means is if you have IoT and microcontrollers, FPGA, so your smart thermometers and other things like that, or your mobile devices, they're really attractive because they have such low standby power. And the same stands for the increasing amount of smart cars and sensors and electronic systems that goes on your automotive. But while EV themselves aren't used as much for high-speed computing in terms of caches, embedded memory in general are used for, as I've said before, those small, fast, but expensive memories. I want to zoom in a little bit on the automotive side. You don't really need to read the whole slide. I just wanted to bring your attention to how much electronic system there is in a typical car. And as you can see in kind of this graph on UMC, every one of these systems requires some sort of microcontroller that is dependent on your ENVM devices. And one of the most popular ways to do ENVM is called EFlash, which I'm glad my colleague, I guess classmates have talked about in the previous two presentations, so I don't have to go over their physics. But the two challenges that they're facing is really the fact that EFlash requires high drain voltage, and that limits your lateral and vertical scaling because you need a certain size tunnel oxide and channel length or source strength depth to make sure your device actually function. And you can see here on the right, I don't know if you can see my mouse, but this is like one pretty cutting edge EFlash implementation where they scaled vertically by going to this more flat structure on the right. And that's called SG monos if you want to look it up. So that gets you to about 28 and 22 nanometer. And maybe we can push to 16 and 14 with EFlash. But the more that you push this, the more mass that you're going to need. For example, the monos one I just showed needs about 9 to 18 extra mask on top of the ones you need for CMOS. And if you ever like seen the price tags on these things and the yield problems that it causes, you know why there's a lot of concern for complexity. And I'm not going to go over this slide again since you just heard about this twice. But again, STT-MRAM uses MTJs, and the fact that you have spin transport torque as electron flows through your MTJs. But I do want to talk about in more detail the key advantage of STT-MRAM in terms of for embedded memory, and the fact that it's non-volatile. And this is because STT-MRAM uses spin-based magnetic storage instead of capacitor in DRAM or flip-flops in SRAM. And what that means is you don't need to refresh your capacitors when they leak, as in the case of DRAM, and you get really low standby power. And it has theoretically unlimited endurance since there's no actual atoms being moved around during your read-write process. However, there's still possible leakages that will affect your true endurance. But as you can see in the chart to the right, people have demonstrated read-write time to 22 to 30 nanoseconds. And that is quite impressive when you compare to the rest of the technologies being considered for NVM these days. As my classmates have said, SRAM, DRAM are generally, and EFlash are the most competitive, but you can see that STT-MRAM has the advantage of being high endurance compared to EFlash, really low write time, and the fact that it is non-volatile. And that's where STT-MRAM really shines. But of course, it's not perfect. And one of the scaling concerns that we have is this trade-off between power, speed, and stability that you see in STT-MRAM. And that arises from the fact that you're really competing with thermal fluctuations as you try to push your drive current, push your switching current down. I'm not going to go over too much of the math here, but you can see how this IC0, which is your switching current benchmark sort of, scales with your magnetic anisotropy. And you can think of this as the more stable you make your bit, the higher the energy barrier, the more current you're going to need to drive it, which makes sense. But that's kind of bad if you try to go below the IC9 and kind of cheat a little bit with your power consumption. You see here the two dashes line are actually the physical limits of two competing processes. The top is called ballistic swinging, which is where STT is dominating your switching. But the bottom, this more linear regime, is actually thermal fluctuations. And you see the switch comes off around when your current equals IC0. So if you try to push below 1, you're going to find that you're getting random error switches from thermal fluctuation, as you see here in red and blue. And actually, I want to go back a little bit. What that means is not only do you have a limitation on your current, you have a limitation on your switching speed. And you can see here the difference being shown in the red and the blue. Of course, the longer the pulse, the less error you get. But how much is good enough? And that is something that Worledge and Kent has been working on a lot. And I'm sure they will come up with amazing solutions in the future. And I want to move a bit on the more practical manufacturing concerns. First, any MRAM process, if they want to be competitive in embedded space, needs to have a good temperature tolerance, just so you can actually make these chips with CMOS and other technologies. And that here, the second point is actually one of the biggest challenges with embedded memory in general. How do you integrate this with the rest of the processes? CMOS is such a dominating technology that you have to make sure it works with it. And I already touched a little bit on complex mask and yield optimization for EFlash, but the same thing applies for MRAM. And I will show you something from IBM that really drives that point home. And so one example of a practical concern would be your MTJ scaling needs to be small enough to fit between metallization levels in your conventional CMOS device. If it's too big, you're going to have to scale up your CMOS, and no one wants to do that for memory. And the third problem here is non-traditional materials. You can see here on the, this is just an example empty stack used for MRAM. all this different kind of materials actually gives non-volatile byproducts when you do reactive ion etching. And if those byproducts just fly everywhere, and they can become defect sites at different parts of your device, or even short entire metallization structures. Terrible, terrible manufacturing concern. So in the future, if we want to solve these problems, first we need to, one way to do this is increase magnetoresistance. By Woolridge and Ken's estimation, you need to get really above 300% to enable larger memories and faster read-write times. As we talked about temperature tolerance, you can one of the applications I mentioned today was used in cars. If you have hot engines burning all the time, your chip needs to be able to withstand temperatures of up to 200 degrees Celsius is kind of the standard there, so that it doesn't melt when you're actually putting in a car. And I'll talk a little bit more about scalability in the next slide, but we've seen that IBM has announced a 14 nanometer node, and TSMC and Samsung are both investing heavily and have actually announced production for MRAM as a replacement for the EFlash ENVMs. And the last thing is the infrastructure and technology ecosystem around MRAM still needs to be built up, especially for higher throughput usages in 300 millimeter applications, because we know if you don't scale up, no one's actually going to use this thing in industry. I just want to touch a little bit on IBM's 14 nanometer because I thought it was pretty cool they were able to scale down this much. You have a pretty typical free layer and pretty typical, MTJ structure. But what they've been able to achieve is 4 nanoseconds write time on a 160 nanometer MTJ pitch. And as you can see here on this right, this means you can fit your MTJ here in green between the M1 and M2 metallization layers of what you use in CMOS, which is kind of down here. You see your FinFET CMOS. You can directly embed it between the metallization layers to get truly scaled embedded memory. And this represents a major step towards last level cache, which I talked about as kind of like the golden ideal memory. This is like the hardest thing to do, but also the most exciting part for MRAM, really. Oh, I did want to show this slide because someone had a question about MRAM applications besides just embedded. You see here's increasing difficulty. Of course, the easiest that I see right now is just use it as a standalone. But I talked a lot more about embedded in this lecture, but if we can get the write time down and the read and write time down and the actual embedded integration with the rest of CMOS process, like what IBM has kind of been doing, you can get eventually to this last level cache, which is, as I said, the fast, expensive, and small memory that embedded is really good for. So yeah, thank you for coming to my talk, and I'll take any questions.
Thank you. Okay, any questions for Teddy?
So I guess I was wondering, like in terms of EFlash versus MRAM, like EFlash, I guess flash RAM nowadays is 3D stacked and has like really good density and scaling. So I was wondering how MRAM would compete with that in terms of like fabrication, like on like a 3D scale or something, like if that's even possible to achieve that, like how Samsung is able to like do their 3D VNAND and all that.
Yeah, so you're absolutely right. EFlash looks like it's still the dominant technology in the current node. And I kind of just went back to EFlash slide here, especially this SG monos. You see how they went from 120 nanometer pitch to even lower. I don't recall the exact number on this, but compared to what I said for IBM, which is 160 nanometers, yes, EFlash is still advantage in the current stage. The biggest problem that we see with them is just the scaling concerns. This monos has shown to work at 28, and it'll probably work for 22, but if you try to squeeze it a bit below that, the manufacturing complexity just goes off the chart. As I say, it's at 28, it's already 9 to 18 extra masks. And if you try to cut it down even more, you're gonna waste too much time and money on the embedded memory part for it to be really viable.
Thank you.
Cool.
We have time for one more question.
Are there a lot of performance enhancements for increasing the volume of EFlash storage?
Yeah, so SG monos, there were 3 major routes being undertaken for EFlash. SG monos is kind of like I think the most promising one that I picked out of the 3 to talk about here. But I think all 3 faces the same limitation in that their drain voltage just by the nature of that device is just high. And so you just have trouble scaling down channel length and your oxide. And one thing I forgot to mention is for MRAM, you actually don't have this problem. In fact, you want low voltage because high voltage actually damages your MRAM device. So that is kind of an inherent advantage STT-MRAM has, and that's why it seems more promising for lower nodes.